Well, hello again, and welcome to today's lecture. This is lecture 31, I believe, and we are on the topic of gears. Today, we're going to talk about planetary gears. Let me share my screen, and we'll go from there. So, screen being shared, and let's turn off the video. And I'm gonna move my microphone. All right, I moved my microphone a little bit closer to myself, but please let me know if my voice decayed or you couldn't hear me well. What is a planetary gear? So we talk about gear trains, and we said there are three types. We talk about the first two types, the simple and the compound. One common feature of simple and compound is that the center of each gear is fixed. By fixed, I mean it's a fixed joint and the shaft is not moving anywhere. Like in this setup, in example 4 that you saw, we can say that each shaft is on a bearing. Like the shaft for gear 2 is on a bearing, which we can, in a schematic way, we will show it by this sign, like these blue lines, indicating that gear 2 is on a shaft that is fixed. 3 and 4, they are on the same shaft, and of course they are on a bearing, or maybe 2 bearings, and they are also fixed. Gear 5 also is fixed. Like the center of gear is not going anywhere. The gear is just rotating around the center of the shaft or the center of gear. This is the characteristics of a compound gear. The same with simple gears. Let's move back to one of old simple gears that we had. This is all compound. So again, as you can see, the center of gears is fixed. All right. But one characteristics of planetary gear is that the center of some gears, not all of them, can move around. Let's again move back to the previous example. Maybe we can have this set up so that gear 3 and 4, they can rotate around like this main shaft. And if we have that scenario, then we will call the train or the gear trains a planetary gear. There are a lot of applications for planetary gears, and the good feature that they have, they can transfer large torque or very high speed. So the gear ratio can be very high. I posted 2 videos, short videos last night. I hope you watch those, and they show the application of these gears. Because those have good animations, it's better than me talking. Here is the first 30 seconds of one of them. So planetary gear, there are the sun gear, the green one, and then we have the planet. And of course, here we have the carrier. So these are the components. The sun, it's the one at the center. 3 gears, which we call them planet, the ring, which is around, and then the carrier. We can have combination of motion, as this animation shows, like this one. You see the sun is fixed, the carrier and the planets, they are moving and rotating, and also the ring. So in this setup, the ring is fixed, and as you can see, the carrier and the sun and the planets, they are rotating. And in this setup, the carrier is fixed. The sun is in the input, and the ring is the output. And they can rotate in opposite direction. So I encourage you to watch those two animations. It explained with great details, and also explain when we have several of them parallel, like this picture, how it works. As I said, the components, the main components are the sun, the planet, the carrier, and the ring. In this setup, I said the sun to be fixed. By fixed here, I don't mean it doesn't rotate. Of course, it rotates, but the shaft is fixed. It's not going anywhere. That's why we call it a sun. It can just spin around itself. And more details on the drawing on the right, which little components also it shows with the bearings as well. A good application of planetary gear is in a stepper motor. If you have an old stepper motor, you can open it up and see inside. And each stepper motor has one of these. And the reason is if you want to transfer high speed or high torque, again, depends on the application. They have low noise, and especially if you use helical gears inside, because inside they can be helical gear or simple gears. And a good balance, because usually we have 3 of them, like here, 3 planet, 1, 2, 3, and it creates a good balance. That's why they are quiet, not too much vibrations, and a good life, because the amount of force is not that much. And, you know, a stepper motor for small CNCs, 3D printers, and so on, we'll use them a lot. So you can easily change direction or change the speed and so on. I let you guys to, if you are interested, you can read more about the stepper motor later. It's not the topic for this course, but definitely one of those things that you need to have a good knowledge for your future works or career, or if you're building and making things. So you can study on your own. And here is, again, the animation, which you can watch on your own. So what we need for this course is, similar to other gears, is knowing about the input and output gear ratio or speed ratio. But first, we need to know how we can show them symbolically. You saw in previous lectures that a gear, instead of showing the gear, one way is, let's say, if I have a cross section of a gear, if I show it like here, let's say gear on a shaft. Maybe if I use a, yeah, let me use this one. No. So if you have a gear being centered on, let's say, a shaft, sometimes we just simply show it like this. Like this is our gear and these are the teeth. And then we say, well, this is the main shaft. Sometimes we may just like have this sign to say that this is on a bearing, or sometimes people show it like this way. This is the gear, and then a little things here, a little one there. So this is like a schematic way of showing gears, and like this is all the centers, right? Which you need to be familiar with. It depends on the problem, or in the future when you read a drawing of, let's say, a gearbox or something, you need to know how to read it. As I said, sometimes we will show it like we show the cross section of a gear, or sometimes we just show this schematic way. Let's now get to the planet gear. It's very difficult to show the circular way. for a simple case like that one may be easy, but usually we use the schematics. So that's why you need to know how to show them. And it's easy to figure out, right? The planet, you can see the planet. Let's start with the sun. So this is the sun, right? The one at the center. And then we have the planet, the other gear. And then we have the ring, all right? So be careful the way that we show the ring. The ring is a internal gears, right? And then we have the carrier. Of course, in practice, the carrier is not possible to build it like that way. It's just a schematic way to show it. More like in this picture, we think this is as if it is like a bent wire, right? But it has width and thickness. But this is the schematic way that we show it. Maybe the picture and the view on the left shows a better representation for a carrier. Okay, so that's one way to show the schematic of a planetary gear. And again, pay attention to, please, where the carrier and the ring, they have been connected. So inside the, let's say the ring, we can have a bearing. So the carrier, now you can see it pass through it, right? It's over here. We can have it there. And depends again on the setup. We may have, let's say, the ring also rotating. Then we have the whole things on a bearing. All right, so the ring now can rotate because it's on a bearing. But sometimes the ring might be fixed, and we will show it by like this sign here at the bottom. So it shows that the ring is being fixed. So it means ring is fixed. It's fixed, of course, to the ground. But this sign, it means the ring is rotating. Or ring can rotate, right? So again, in this setup, the sun can rotate. And obviously, this is what we want. And it is on a bearing, right? But it cannot move, let's say, around. The planet can rotate around its center. And also, it can rotate around the sun. The ring can rotate. Any of them can be fixed or they can rotate. They can rotate in any direction, depends on the problem. When we solve problems, we need to state that which direction we are looking at. Let's say, we'll say we are looking from the right side. So, and we need to be consistent. If this is our eyes, if you're looking at this gear, then we consider one direction positive, let's say clockwise to be negative, counterclockwise to be positive, and we have to say that we are staying in one direction. Then we can say, for example, the carrier, let's say the carrier is rotating with omega c, and you can tell me it is clockwise, so it is negative. The ring maybe rotates counterclockwise, so it is positive, and depends again on the problem, we need to solve it. Then the sun, let's say it rotates counterclockwise, and it is positive. If we look at one side, right? If you go to the other side, if you look at these gears from the right side, then you may say, no, it is rotating clockwise, right? But we need to be consistent and just one view from one side. Always, doesn't matter left or right, but because a simple negative or positive will change everything. So I said the planetary gear has a 2 degrees of freedom, and you need to figure out why. You can think about it later on your own. Of course, you need to use the relation F3n minus 1 minus sum of all the constraints. Try to solve it to make sure that I am right here and the planetary gear has 2 degrees of freedom. What does it mean for us? When we say it has 2 degrees of freedom, it means when we solve planetary gear, we need to have 2 inputs. So the problem needs to tell us whether the speed of carrier, the speed of the ring, or the speed of planet and the speed of the sun, in order for us to solve the unknown. Or maybe sometimes the speed of one of them is 0 if they are fixed, like in this setup, if the ring is fixed. So here are the example of planetary gears. So they can be a more like, let's say, complicated shape. Let's take a look at them and see if we can figure them out. Let's start with the top picture, the one on the left. Now I want everybody to pay close attention and see if you can identify each gears. So let's start with S1. So this is S1, right? S1 is the sun. It's fixed. Then we have P1, which is like planet 1. It can rotate around S1. And P2 and P1, they are on the same shaft. So it means their shaft has the same speed when it rotates around. And they have also the same rotational speeds, similar to compound gears, right? And then P2 is attached to another sun, which is S2. So I want you to visualize this gear and in your mind and see if you can think how it's going to work. Maybe to simplify for yourself, ignore the P1 S1 for a moment. Okay, ignore P1 S1. Maybe if I can hide them for you. Oh, doesn't hide them for you. Let me do this trick, make them white. Okay. So thank you, Microsoft. So I guess you should be able to visualize how this system works, right? P2, S2, and the courier, similar to the previous one. Now we will add the second part. Second part also move with this motion. So the one in the middle is a little bit more complicated, but again, if we go slowly from S1, we can figure it out what's going on. So let's take a look at S1, P1, and the courier, right? You can visualize, just think about S1, P1, and the courier. Ignore this part, and everything's around here. Okay, so we have a sun, S1, we have the planet, P1, and we have a carrier, which carrier shows the rotation. And by the way, this like sign that you see on the picture here or there, it means a bearing, right? So it means the shaft is on a bearing on this carrier C, or it is just a simple joint. If I move back to the previous picture, this is like in a schematic way, we'll show it just by one little joint here. But of course, in practice, this is a bearing, and in a side view, we'll show it that way. So I guess you can visualize what's going on here, S1, P1, and the planet C. Now let's get rid of these guy, and I had another one there, and I had another one there, right? Okay. Now we have a little planetary gear inside this system, which is like S2 and P4, right? You can see S2 and P4. Can you visualize those for me? S2 and P4, and again, another carrier. You'll see there is another carrier here. Where is the things that hide the stuff? Okay, it's here. So this is another system, S2, P4, and of course the carrier, this little carrier here. Okay, simple. And let's get back. And now the whole things are moving together. It's hard to visualize now the whole things because now it can be a very complicated motion. Each of them can rotate in one direction. One thing that I want you to pay careful attention is that in planetary system, the center shaft, when the carrier is attached, like this one here, let's draw them separately. They are all in one line, right? So you cannot, for example, let's take a look at the first one on the left, which is simpler. So you cannot have the Sun 1 and Sun 2 each have their separate shaft. I mean, not being in the same line or collinear. It's not possible. They have to be on the same line. Independent, they can have their own rotation, but they have to be on the same line. So you can later think about, visualize if, for example, S1 has a shaft that it's a little bit higher or lower, if it's possible that for this system to move, it's not possible. And please do the same things with the picture on the third one. It's very simple, you can figure it out. Now we have two carriers, C1, C2, and S1, S2. And be careful, the ring now is just one gear, but it has, you see, the ring here. There are two gears, let's say that. Let's say two internal gears being attached, being fixed together, and they made this ring. So they can have their own number of teeth. So different number of teeth. Of course, since they are fixed, they are welded together, they're all in part of one thing, the ring, they have the same speed, but it doesn't mean that they cannot have different teeth. So that's another thing that they need to be careful. All right. The picture in the middle, we have two carriers, but the carriers, these two carriers, they have been welded together, so they have the same speed. Okay. So this little carrier and this bigger one, they're welded together, so they have the same speed. All right, so the reason that I emphasize on this, because again, similar to any other dynamics problem, before you solve any question, you need to have a good visualization that how the system works. If you cannot visualize it, then it would be in any dynamics or any problem in mechanical or manufacturing engineering. I remember when I was in high school and we wanted to decide to go for a subject in university, and we were told that you need to be able to visualize a good, let's say, 3D modeling of the universe. By universe, I mean for different mechanism or different machines. You can visualize them in your head, how they are moving, and it is true. Some people may not be good at that, but for them, let's say if they are in mechanical engineer, then instead of going to the category of solid mechanics, maybe the category of fluid mechanics is better fit for them. In manufacturing, again, there are different branches, but if you are willing, let's say if you wanted to go to automation, when there are robots moving, and the mechanism, designing machineries, or analyzing the motion of, let's say, different machines, then definitely you need to have a good visualization. But let's say if you are in manufacturing, but you are interested in studying the characteristics of a material being casted, let's say when you cast a material or when you machine something, then it doesn't need that skill for visualization. Anyway, you need to have a good understanding of how things are moving, especially for a course like dynamics. So let me check chat to see if there is a question. So Felix, what happened to the rings in the first two pictures? So yeah, there is no ring here, right? So we can have a setup with no ring. Let me draw something for you. So not like necessarily we do not have to have always the whole components. Like if I have two gears like that, so, and let's say this is the center of the first one, the center of the second one. If the center is fixed like this, of course, this is simple gears. Shaft 1, shaft 2, they are all fixed at the center. So, but now let's say I fix this shaft. Okay, so let's call this one gear 2 and this one gear 3. So let's say gear 2 is fixed to the ground. It can spin around itself. Gear 3, rather than fixing it to the ground, let's say I make, if I can find, I make a carrier, which basically is a link. Okay, something like that. And now like let's say if we call this center O2, O3, now O3 can move, right? And we don't need to have a ring. It can move. So we can have, let's say, 2 rotating that way. And maybe, so this is omega 2. And then, oops, not bad. Let's say I want to, and this is omega c, or they can be in the same direction. And then omega 3 has its own omega and it's rotating, which the next slide we are going to learn how to calculate that. And we don't need to have a ring. So this is a planet system and it works. Now, if we say, okay, I need to have a ring so I can get an extra motion or I do extra things with it, yeah, I'll add a ring and the ring has to be internal gears. All right. So then let's write a title for this one. Planetary system, planetary system with no ring. Okay. So I hope that answered your question. And let's see. How do we know how many planets are used from the drawing? So that's a good question. When we solve problems, so maybe it is also other students' question. Let's move back here. So take a look at this setup. This system can work with only one planet. So let's see, all right. So if I just connect these two with a carrier, then the system is good to go. But the reason that we add 3 is to balance forces. Sometimes people add 4, sometimes 5 to, let's say, have less stress on these smaller gears because you divided the force between them. Okay, so in a question, when we solve for dynamics and the motion, maybe the picture just shows one of these planets. That's okay, still we solve the problem because the other two has no effect on the, let's say, when we calculate the velocities and the gear ratios. All right, but the question typically, like this one, it shows, of course, 3. In practice, always there is 3, but when we go to the schematic, it may just shows one planet like this one. If I want to solve the same problem, like here, it doesn't matter if I have another planet here, another planet there, because they are going to be connected to the same. Where is my line? Oh, it's here. They can be all attached to the same carrier, like same, and they have the same speed and everything is the same. So the system is symmetric. So sometimes the picture shows, most of the time it doesn't show. Like in this picture, it doesn't show the number of planets. But in actual drawing, it states what's going on. Maybe there are extra planets, how many planets they are, and so on. In the schematic, you will see a drawing like that. So let's do a practice together. The picture at the bottom, I want everybody to have a piece of paper or something and try to draw the schematic of this gear. Okay, so similar to what we did at the top, and identify the sun and the planet. And I'll do the same, but I give you a minute to think about it. While you are thinking about it, I draw extra stuff here. So that line there, so we know what's going on. Almost. So that one is there. Okay, you guys finished? Should be easy, right? Be careful when you draw the schematic. There is like a small difference between gear 4 and 3, right? Take a look at the number of teeth, 30 and 28. So, and you know, when you see the number of teeth, it sort of indicates the diameter, because all the gears in a gearbox has to have the same pitch or the same module. So again, when you solve a problem or in a drawing or somewhere, most of the times people use the term pitch, which defined as n, number of teeth, divided by the diameter. Sometimes, mainly in SI unit, people use module. And you need to be familiar with both of them. So pitch n divided by the module d divided by n. And be careful about, like, of course, unit. But as I said, like, people usually they don't, when they say pitch, they say the pitch of this gear is 10. But if we want to be accurate, we'd better say, state the units and say the unit is 1/millimeter or 1/inch. And this one, of course, can be just inch or millimeter. But the module is mainly using SI unit. It's not that it's not common, and people show it with capital letter P, and this one people show it by lowercase m. Okay, so, and keep in mind, two gears working together, we call them, they are meshed together. They have to have the same pitch or the same module. In a gearbox, necessarily they don't have, like, let's say all the gears, they don't have the same modules if they are on a different shaft. But it's very weird if you have a gearbox and the gears have different modules or different pitch. So as a common rule, whenever you see a gearbox or you design a gearbox, your assumption should be that all the gears, they have the same pitch or the same module. And similar to the assignment or the quiz that you did, quiz 10, we can use this information to find the missing information for the number of gears. Okay, so let's get back to this one. And we should be able to draw the schematic. Let's start from the left and find our way to the right. So if I want to follow the same schematic rules, so this is gear, should be gear 5. Where is that thing? Okay. So I'm sure you got the same things. This is gear 5, right? We show a little shaft there. And, oh no, that's not gear 5. Gear 5 is here, the big one. And here, of course, we better show this little center. And then we have the other gears. Which is the small one there. And this gear goes here. That's a boring job, right? But at least we need to do it for one. So then later when you solve problem, you can easily figure out which one is which. Okay, so far good. I hope I didn't make a mistake. Yes, it seems right. And then this guy is there. And this is the center for this guy. Okay, so that's for that. And now let's use another color maybe for the carrier. Let's show the carrier with black. So the carrier, it seems that it goes at the center of these gear 2, and then it goes up with a little longer. And it goes up and it holds these shaft. All right, so success, I guess. So this is gear 5, this is gear 4, this is gear 3, this is our carrier, and this is gear 2. All right, everybody agrees? with this. And to be like more accurate, we'd better say that this is being fixed, obviously, and also main shaft here is being fixed. Or by being fixed, I mean it's on a carrier and it can rotate. Good. I hope you guys got the same things. I'm going to wait here for 30 seconds so you guys can check the notes or add notes for yourself and make sure that you follow every step. Just pay attention again. Carrier C is passing through the center of gear 2. So gear 2 can have its own independent rotation. Okay. Sometimes I've seen a student make mistakes. Since they are on the same shaft, they make mistakes. So that's why the picture on the left, it's more clear, right? So omega C can have its own speed because it is in its own bearing. Omega 2 can have its own speed and its own direction. They can be like omega C and omega 2, they can be the same direction. And omega 5, of course, it can have its own direction, its own speed. And 3 and 4, they can rotate around this, like this shaft, of course, has a rotation. And then the whole things also rotates. I'm trying to do a good drawing. Okay, so if I want to indicate the speed, if you notice today, we'll just did all the setup and it is important. Be careful about it. This is omega 3, which is equal to omega 4, right? And this is omega C, right? Because like the center of this shaft is attached to this carrier and carrier is rotating with omega C. This is a simple picture, but please study it carefully after the lecture. Make sure that you understand every aspect of it. So then later when we will do the calculation, you can understand what's going on. All right, any question here? I'm gonna stop for 10 seconds so you guys can ponder around that and make sure that it's all clear. Because if it's not clear here, then we'd better not move forward. Because this can be really confusing when it gets to calculations. Let's say somebody gives you a gear similar to the picture on the top, the middle one, with bunch of information for speed of sun 1, speed of, let's say, carrier, and they ask you to find the speed of sun 2. So you need to know which one is which and how they are rotating. So if you're good, now let's do a quick calculation and see how we can analyze it. I'll start now so you have an introduction. Hopefully, if you haven't watched those videos for planetary gear, you go and watch those 2 videos and be ready for the Friday when we'll do actual calculation. But here, let's just do very, very basic calculations together, okay? So since the topic is a little bit confusing, let's start with a simpler case. Before getting to this case, let's say if I have 2 gears in a simple setup. It's not going to happen. So let me. Okay. If I have these 2. So let's call this one gear 2 and this one gear 3. And we know if their center is fixed, then omega 2 over omega 3 is minus n3 divided by n2. We know that. It's super simple, right? Let's say simple setup. Now right here, let me draw a shaft between them in a different color. Okay, this is a shaft between them, but this shaft, imagine that it's being fixed. So this is C, the carrier C, but the carrier C is being fixed. If C is fixed, it is fixed to the ground, right? If something is fixed to the ground, you can visualize that it doesn't even exist. So if we have that scenario, we are going to have a simple system. A simple system. But what if it's not fixed? So scenario number 2, if C is not fixed and can rotate, then what I will do, I will write the relative motion. Remember those very old days when we talk about relative motion? I will write, instead of omega 2 over omega 3, I will write omega 2 with respect to C over omega 3 with respect to C. And if you recall from old days, when we talk about something with respect to another point or another thing, it means we consider that things to be fixed. So if I write then that sentence, the moment I'm writing this one, it means that I'm considering to have that guy, right? Because we are considering everything with respect to C. It means C is our reference, C is being fixed. So then this side stays the same. Okay, the only difference is, and this is the important part that I want you to pay attention for just 30 seconds, is here we have omega 2, we have omega 3, each one has its own velocity. We just calculate the ratio, good to go. But here we have omega 2 with respect to C, omega 3 with respect to C. And if you recall again from old days when we talk about relative motion, when we have something with respect to something, maybe I'd better write it there. We have to write it as omega 2 minus omega C, omega 3 minus omega C. Remember when we talk about, let's say, VA with respect to B, we wrote that VA minus VB, right? The relative velocity. The same with when we say omega A with respect to omega B as a vector. Omega A minus omega B, relative velocity or relative angular velocity. This is the same things. We are calculating the speed of omega 2 and omega 3 with respect to the carrier C. So to simplify this relation, now I've got this guy. Omega 2 minus omega C, omega 3 minus omega C is equal to minus N3 divided by N2. And this is not a formula. We are not going to use a formula like this because every system can be different. This is just the fundamental here. We will discuss it on on Friday. But please review these lectures and these notes and this relative motion. Try to understand it. And then we will solve it for a complete planetary system. And then we'll solve example 5 and example 6 So you could master this topic, which consider to be one of those confusing topic, and many students I've seen, they give up and they say, like in the past, because like the textbook or maybe some lectures or some teachers, they do not teach it like in this way. So you could follow and could solve the problem. See you guys all on Friday. Have a good day. And I'm gonna stop here, but I can stay in the room for a couple of minutes if you guys have any question. I'm gonna also check the question in the chat to see if there is anything. No, everybody's good. So I hope I answer all the questions and we're all good to go. Let me start and record.